All right, first let's talk about arithmetic sequences and series, right? Arithmetic means they have a common difference, all right? For example, let's say I have something that says 2, 5, 8, 11, 14. I look at that and I say, I notice it looks like I'm adding 3 each time. And the way I can find the common difference if it doesn't jump out at me is I would take this term, 5 minus 2, 8 minus 5, 11 minus 8. So notice, those are all 3. I'm adding 3. It's an arithmetic sequence with the common difference of 3. Well, it's easy enough to write the rule because there's a general rule that says you just take the first term, a1, and you add d n minus 1 times. So I can write this rule, an, for any n I want, any position in that sequence. I take the first term, a1, plus 3 n minus 1. And there's my rule, okay? Now, I could distribute that if I want and simplify. I'm not that concerned about it. So let's say we had one. This arithmetic is pretty straightforward. You just have to recognize there's a common difference. The next one is geometric. These are, this is 10.2, 10.3. Geometric have a common ratio. So let's look at an example of that. 2, 4, 8, 16, 32, blah, blah, blah. Now, let's say it didn't jump out at you what your common ratio was. Well, just like I did up top, I take 4 divided by 2, 8 divided by 4, 16 divided by 8. That looks like I'm multiplying by 2 each time. So I have this common ratio of 2. All right, so there's a general equation for a geometric. I'm sorry, they keep hitting my keyboard. an equals the first term times the common ratio raised to the n minus 1. So this one would be an, that means for I want any term in this sequence, I use a1 times 2 raised to the n minus 1. All right, these are known as explicit rules because they're based on position only. I can find it for any n. Remember, we talked about recursive rules. Recursive rules are based on the term in front. Based on a prior term. Usually the one right in front of it. That's a recursive rule. And those look like, on your equation sheet, let's do this. On your equation sheet, you have arithmetic and geometric. All right, so our explicit rule looks like this. Right, those are the ones. I don't know why this thing doesn't want to write when it's supposed to write. D n minus 1. Geometric, on the other hand, is a1 times r to the n minus 1. Now we also have a recursive. So recursive looked like this. an minus 1, that's the term in front of the one I'm looking for, plus d. Isn't that what a definition of an arithmetic sequence is? I'm adding d each time. In addition, I have to give the first term. Because notice, if I was trying to find a1 here, there's no term in front of a1 to find it. So I have to give a1. Geometric, on the other hand, blah, blah, blah. Recursive is the term in front of it, right, times the common ratio. That's what geometric is, times 2, times 2, times 2. Again, I have to give a1. All right, now we have sums that we were talking about too. Let's talk sums. I want to sum an arithmetic sequence. I can only sum a finite arithmetic sequence. And the equation was the number of terms I'm summing, the first term of that plus the last term of that over 2. You'll see it written like this. Sigma from 1, I'm going to use I, 1 to some n. We don't know what the n is. Could be anything. And then the arithmetic rule usually looks like, right, a1 plus dn minus 1. Now, for geometric, I can sum a finite, but I can also sum an infinite, but I can only sum an infinite if that common ratio is less than 1. I can sum a finite all day long. So here it would be from I equals 1 to some n of, let's put in our a1 times r to the I minus 1. That's a geometric rule, right? And that sum equation was, if I'm getting this right, a1, 1 minus the ratio raised to the number of terms over 1 minus the ratio. This is on your equation sheet. Now, if I was summing from 1 to infinity of that same type of thing, remember, I can only do it if r is less than 1. That means it converges to a real number. If r is greater than 1, it diverges. Diverges means it heads toward infinity or negative infinity, okay? And this equation was a1 over 1 minus r. All right? Now, 12.1 actually gave us some things that were neither geometric nor arithmetic. So let's try a term. Lots of times these will be based on the ends. So let's say I have a term that looks like this. This one would actually be geometric. I'm trying to think of one that, or arithmetic, excuse me. How about, so let's say you looked at this one and you couldn't figure out, these are the terms, right? So there's no common difference, there's no common ratio. Well, I like to write my ends, the actual position above it. This is the first term, the second term, the third term, the fourth term, the fifth. All right, now see if you can relate the term to its position. And I think you would see it, that an is actually n squared, isn't it? N squared, in this case. This is explicit. It's based on its position. All right? Now, on your equation sheet, too, you do have some equations where you can find from I equals 1 to n of 1, gives you a formula. From I equals 1 to n of I. So here I'm adding 1 plus 2 plus 3, whoops, and so on. That was something like, I don't know, I really want to write when I want to write. Equals n plus 2. Look at your equation sheet. Finally, you have one that looks like this. Let's say I'm summing this term from something 1 to n, not finite, but infinite. I mean, not infinite, but finite. We're doing a finite sum here. It's n plus 1, 2n plus 1, all over 6. So those are on your equation sheet. So take a look at this and see if you have any further questions.